Good afternoon, students. Welcome to our webinar session. So now we are discussing electromagnetic induction, chapter number 9, related to concept. Right. So you might have discussed with the basics, right? So related to that only, we are going to do some problems. So when once you are comfortable with the formula and all, then you can able to solve. So practice more the concepts and related to the formula. Here, the sum of the synopsis means majorly just from these synopsis, and anything is left over that we'll discuss in the next class. That today we'll mostly try to cover these synopsis. See a magnetic flux linked with a coil of area A in magnetic field, right? B, then QM means what is sorry, pi M. Pi M is not what is a flux, that is magnetic flux linked with the coil is asking of radius A. So the formula is VA cos theta, right? In the vector form, it is V dot U. So dot product. Then Faraday's laws. There are two laws are there, right? So Faraday's laws induced EMF. You should be very cautious about these laws, and very important. Once you are strong with the concept, then only you can able to solve these problems. So how this induced EMF will be generated. So that is very important. And in that two laws are there, and here E is equal to means sometimes actually it is an E. EMF is a electromotive force. So E is equal to minus N dot d pi by dt. Look at that, pi is already discussed earlier. It is a magnetic flux linked with the coil of area A. So here that flux is changing with respect to time. So that gives the induced EMF. And here negative sign indicates that always both are opposite in direction. Right? I mean, once it is decreasing, then it will be increases like the vice versa cases. So where pi is the magnetic flux linked with the one turn, and next one is the current induced. Current induced. So I is equal to E by R. Actually, E is a potential. Okay, E is a potential, right? Which is developed when there is a magnetic field is changed. So this is usually means actually we call this as an EMF, but it's a potential, right, between means two edges or two ends of the conductor. So if that current means conductor is closed circuit, then the current flows. So that's what is an expression here. Current I is equal to E by R, and E there we got minus N delta pi by delta T, right, and N by R here. So N is of course is a number of turns over there, right? So here the charge induced Q is equal to the charge, right? So charge is equal to N delta pi by R, right? That is equal to delta N pi by R. So is nothing but delta pi by R. If see here pi is N pi is effective flux linkage. It's a linkage, right? How much link is enclosed with the given circuit or coil as per the situation. Now EMF induced in the moving rod, induced EMF, okay, EMF induced in the moving rod is expression, okay, is related to the rod here. So BVL sin theta here, BVL sin. Here sometimes B when we it's magnetic field will be given, sometimes horizontal magnetic field. Based on that, see theta is changing, no, here theta is changing, so that's why the B is also changes either x-axis, y-axis, that is x component or y component. Right, so here, yeah, it's given. So Bn is maybe B sin theta component is magnetic field to be normal, okay, and theta the angle between the velocity and the Okay, the field. So here is that, and we'll move to the next one. Induced in the rod of length L moving in vacuum magnetic field. The same rod of length is moving in uniform magnetic field. Okay, the same rod when it is in water. Right. So the expression for the induced EMF of a rod of length L moving in a uniform magnetic field. Right. So for this already you might have derived in the morning that E is equal to BV. Okay. If it is in a linear one, it's a V. If it's an angular one, omega L square by 2. Right now, EMF induced between the center and the rim of the disk rotating in uniform magnetic field. See, all these are the situations. Okay, the formulae may be limited, but when the situations comes, we can change these formulas as required, so as relevant. Now, EMF induced. See, all these are EMFs only. Okay, but situationally, we are changing this that. The coil rotating in uniform magnetic field. Okay, so it's a sinusoidal motion. So then formula will be like this: N B A omega sine omega t, right? And current in the coil of motor, for example, motor is there. So for the motor, I is equal to E minus E into R. Okay, so where E is the applied EMF, right? And E is the back EMF, and R is the coil resistance. All these will come into the actually the motor concept. And is very, very, very important on this 10th one, the more number of problems will be asked, that is called inductance. Okay, so self-inductance, then the effective flux will include with the, actually after derivation we'll get this one. Pi is equal to Li. Okay, so of course L is a constant here. Actually pi is directly proportional to I here. So here L is a proportional to constant. And what is that is induced EMF. Okay, so pi that we know is changing with respect to I. So here is this. The rate of change of pi is epsilon is equal to minus L and di by dt. So work done on establishing the current in a circuit from O to means 0 to I ampere. This is the thing. Okay, so I is changing. Right, so these are just I have given only major basic formulae. And if the next class is permitted, then we'll continue with a few more formulae. Okay, now we will proceed to solve some problems on this. So a conductor circular loop is placed in a uniform magnetic field. I'm repeating, a conductor circular loop is placed in a uniform magnetic field B is equal to 0.020 Tesla with its plane perpendicular to the field. Somehow the radius of the loop starts shrinking at a constant rate of 1 millimeter per second. Find the induced EMF in the loop at an instant when the radius is 2 centimeters. So actually initially the radius of this loop is not given. Okay, so the radius of this loop is starts shrinking at a rate of 1 millimeter per second. Okay, so within 1 second shrinking, the radius is 1 millimeter. Then finding what is asking, finding the induced EMF when the loop radius is 2 centimeters. The moment loop radius come to 2 centimeters, then what will be the induced EMF? Induced EMF is asking. So what information is given? Circular loop placed in the magnetic field B is given perpendicular to the plane. Yeah. So rate is given. So how much rate, with what rate it is changing. Right. Now we'll see the solution here. Let the radius be R at a time. This is very important. So we don't know at what time it is changing, that we know. So what is that? It's the rate. Originally, the radius of this thing is what that we don't know. We are assuming that is R at a particular time t. but is given after, means after shrinking, it became 2 centimeters at a particular time. There, what is the induced EMF? So the flux of the magnetic field at that instant will be, actually, that how much flux is dissipating, that also we doesn't know. So flux at that moment where the radius is 2, that we need to observe. So pi is equal to, means flux is equal to pi r square. Okay, pi r square, radius of that, sorry, area of that loop. Okay, pi r square b. Actually, the pi is equal to b dot a, no formula, right? So there's a d pi by dt. What is this d pi by dt? Change in flux. Why it is happening? Due to the change in radius. Understood? So this is what is the relation. So d pi by dt is equal to, okay, just we differentiated that with respect to t, then we differentiated this pi. So d pi by dt, why it is happening? Because r is changing, remember. As the r is changing with respect to time, this what is delta r by delta t. Delta r by delta t. Okay, so due to this change is already given, shrinking radius is decreasing or changing with the rate of time. That's what, per second. So dr by dt value is given, b value is given, 2 pi that we know, r value is given. Yeah, we can calculate the induced EMF, right? So the induced EMF when r is equal to 2 centimeters is, therefore we can calculate this epsilon, the E is equal to 2 pi, r is there, b is there, and dr by dt value is given. So substituting all the values, we will get the induced EMF. Okay, so observe the problem. In what way we got this? Okay, so if you are conceptually strong, then only you can approach this, right? So finally, we are getting 2.5 microvolts is the induced EMF. Clear? Now we'll go for next problem. Right? A uniform magnetic field. A uniform magnetic field. B exists in a direction. Observe this carefully. A uniform magnetic field B exists in a direction perpendicular to the plane of a square frame made of copper wire. Right? A uniform magnetic field B exists in a direction perpendicular to the plane of a square frame. Right? Square frame, underline that, square frame made of a copper wire. Now the wire has a diameter. The wire has a diameter of 2 mm and a total length of 40 centimeters. Remember, total length of the copper wire is 40 centimeters. Yeah, and that 40 centimeters, a straight wire made that into a square frame. So square means what? All sides will be the same. Then each side will be how much? 10 centimeters. Right? Keep that in mind. And one side length is 40, and the diameter of that is given 2 mm. So what you can get, area you can get. So now the magnetic field changes with the time. Magnetic field changes with the time. That is dB by dt. Magnetic field is with respect to it is changing, so it's not constant field now. Okay, so it's a changing rate is given. Okay, at what rate the magnetic field is changing. So we know whenever there is a change in magnetic field, then what happens? The current will be induced. So find the current induced in the frame. What is asking? Find the current induced in the frame. I hope you understood the problem. Okay, I'm repeating. There is a uniform magnetic field exists in a direction perpendicular to the plane of the square frame made of copper wire. Now the wire has a diameter of 2 mm and a total length of 40 centimeters. And the magnetic field changes with the time at steady rate. dB by dt is equal to 0.2 Tesla per second, and find the current induced in the frame. And here the resistivity of the copper material is given, resistivity. Okay, so resistivity is given. Now we'll go for the solution. So the area of the loop is asking here, area of the loop that, okay, I told you, no, area of the loop is what? 10 length is, no, what that? Wait. Yeah, so diameter is given 2 mm, right? Okay, so I'm searching for that. Okay, so diameter of that wire is given 2 mm. And here 40 by 4, okay, you're getting 0.1. Actually 10 centimeters, converting that into meters, that 0. The area, no? So 0.01 meters square. Now, here the example, okay, so how to proceed this, we'll see now. So if what is asking, induced current they are asking, right? So if the magnetic field at an instant is B, because it is changing, remember, magnetic field at an instant is B, so the flux through the frame at that instant will be, while it is changing at a particular instant, let it be, the flux will be pi is equal to B dot A, as the area remains constant, the area of that frame will not be changed, right? So the magnitude of the EMF, the magnitude of EMF induced will be, the magnitude of EMF induced will be, right? Magnitude of induced EMF. So formula is E is equal to d pi by dt, d pi by dt. And what is actually this formula for this d pi by dt formula is actually pi is what? BA is given here. Okay, so pi is equal to BA. Now rate of change of flux. Why flux is changing? Because the magnetic field is changing. That's what is the problem here. See, right? BA, just we wrote this pi as a BA, but B is changing, not constant. So dB by dt, and A is as usual. So now A, how much A you got is 0.01 meter square into rate of change of magnetic flux is also given is 0.02 Tesla per second. This much flux is changing, this much field is changing. So now you are getting what EMF, that is EMF, okay, electromotive force, that 2 into 10 power minus 4 volts you are getting, right? E value you got 2 into 10 power minus 4. Right now, the resistance of the loop in the problem, the resistance of the copper wire is given, right? So that value is R by rho L, R is equal to rho L by A. Okay, so this is the resistance per unit length of a copper wire actually. So this is the formula, R is equal to rho L by A. Now, look at this. What is 40 centimeters here? Okay, so total area, total length, okay, and area is pi, okay, pi r square. How much r is given here? Look at this, 0.1 m square, right? And this value is already is given in the problem. Okay, what's that? That value is given now, sigma, right? So yeah, so after simplifying this, all the values here, how much is given? Value 1.7 10 power minus 8. So that's what here. Okay, rho into L by A, right? So simplify this, convert that into centimeters into meters here. So 10 into 10 power minus 2, 40 into 10 power minus 2. So what else is changing? Yeah. So pi value is here, 3.14 into 10. 1 into is converting that into meters is given in 1 mm. So simplify this, you are getting 2.16 into 10 power minus 3 ohm. What is this? Resistance. Now coming to current. So current is equal to what? V by R. V. How much V you got? 2 into 10 power minus 4 here. Epsilon, E value. Okay, E value here we got. Because the formula for current is E by R. E by R. You learned this problem, right? You learned this concept. I is equal to V by R. So I is equal to V by R. V, how much you got? Means potential difference, or EMF is how much? 2 into 10 power minus 4 by just now you got the resistance value of that material, that is 2.16 into 10 power minus 3 ohms. Okay, so the 2 into 10 power minus, okay. So it will be 9.3 into 10 power minus 2 amperes. This is current. Okay, so just for getting current, induced current, as per the given information, what information is given? Rate of change of magnetic flux is given, right? And the resistance of what material is given. Okay, sorry, resistivity of the material is given, right? So with the help of that information, we proceed. Now we'll move to the next problem. Magad Express takes 16 hours to cover the distance of 960 kilometers between Patna and Ghaziabad. The rails are separated by 130 centimeters, and vertical component of the Earth's magnetic field is given. Followed. Here, the two railings are there, separated with the 130 centimeters, and that length is given 960 kilometers. And Earth has some magnetic moment. Earth has some magnetic field, right? It has a horizontal field and a vertical field, but is given some component. Vertical component of the Earth's magnetic field is given. How much it is? 4 into 10 power minus 5 Tesla. This is the information. Now with this, what is asking? Finding the average EMF induced across the width of the train. Across the width of the train, means width is nothing but 130 centimeters. Right, and if the leakage resistance between the rails is 100 ohms, then find the retarding force on the train due to magnetic. Okay, so resistance is leakage is taking place. Resistance between the two railings is 100 ohms. Then find the retarding force, means stopping force on the train due to this magnetic field will be. The solution, as the train moves in the magnetic field, remember. Okay, so because this principle, usually we call this as a magnetic trains or bullet trains, no? So this works under this principle only, right? So here the train moves in the magnetic field. It's an example. Okay, the train moves in the magnetic field, a motional EMF. Okay, so that is what BVL is produced across its width, right? Width is how much? 130 is given. Now here B is the component of magnetic field in the direction perpendicular to the plane of the motion. So, for example, the motion of the train is in x-axis, then perpendicular to that is the vertical component of magnetic field that we need to consider. Right now, the speed of the train is given. Velocity is equal to distance by time. So time is how much time is given here? How much it is? Time 16 hours. Yes, 16 hours is given directly. So convert that into seconds. So simplify that. You get okay, so meters here. It should be seconds. So do that simplification. Then after doing that, you will get 16.67 meters per second. Meters per second. So what the speed? At what speed the train is moving now? Is 16.67 meters per second is the velocity, right? Now there's epsilon or E is equal to what is that velocity into B into what is that displacement, means the distance between them is how much? 1.30. Why? It is given centimeters. 130 centimeters. No, convert that into meters. So simplify this, you'll get potential difference 8.6 into 10 power minus 4. Okay, volts. So this is what is the induced EMF. Right now, the leakage current is we know the formula I is equal to V by R, and the retarding force means opposing force. That expression for force is VIL. Here B is there, L is there, length is there. Yes or no? So the force acting on the train will be how much? I is how much? Yes, BIL. F is equal to BIL. So the current, that how much you are getting current here, look at this. current direct value is not given. Here we are calculating I is equal to E by R. E value just now we got here 8.6 into 10 power minus 4. Okay, by R. R value is given in the problem 100 ohms. Okay, leakage is given 100 ohms. Then 8.6 into 10 power minus 4 volts by 100 gives the current here. Into length is 1.3 meters and magnetic field is 4 into 10 power minus 5 Tesla. So simplify this, you will get the value for force in newtons, that is 4.47 into 10 power minus 10 newtons. Here observe the content. Okay, so how we are using formulae in each and every problem. The problem is not simply a one formulae substitution. Here for getting one value we need to use the another formula. So like that it is a as per the competitive point of view, you need to practice both the conceptual and numerics okay concepts related to the formula and all. You should learn this. Now moving to the next problem, a square loop of edge. A square loop of edge having n turns. A square loop of edge having n turns is rotated with a uniform angular velocity omega about one of its diagonals, which is kept fixed in a horizontal position. A uniform magnetic field, yeah, here is the diagram. Very, very, very important. Observe this. Observe this. The square loop of edge is there, having n turns over there, is rotating with a uniform angular velocity omega. See how it is rotating. The axis is along the diagonal. That's what is conveying in the problem. About one of its diagonals, which is kept fixed in the horizontal position. Understood? So the square loop is rotating with their axis is what? Along the diagonal. Now what is asking to calculate? Find the EMF is induced if the uniform magnetic field exists in the vertical direction. The uniform magnetic field B exists in the vertical direction. See, why EMF should be induced over there? Tell me. Why induced EMF should be developed over there? Because what is the reason for production of induced EMF? Because the change in magnetic field. So here magnetic field, just looking at the diagram, the magnetic field is moving inward. But how it is changing? It's not changing. But who is changing here? Area of cross section is changing. Because along the diagonal, this loop is rotating. The loop is rotating. So angle is changing. So when the angle is changing, then magnetic field changes. So whenever the magnetic field is changes, so inside that, the induced EMF will be developed. This is the reason. So remember, induced EMF will be generated only when there is a change in magnetic flux. That is maybe due to the constant, means uniform magnetic field. Even though if the frame or loop is continuously changing, then also the EMF will be induced. So now we'll proceed to calculate the induced EMF for this situation. Right? We discussed in the list of formulae. Okay. Right now the area of the square frame. Okay, it's given area. So all the sides will be the same. That's what is given. Area of the square frame is a square. If normal to the frame makes an angle theta, that is 0, with the magnetic field at time t is equal to 0, and this angle will become theta is equal to omega t at the time t. So what is conveying here? While it is, say the problem is given, the loop is rotating angular velocity, rotating with an uniform angular velocity omega about its diagonal axis. So as continuously rotating, now continuously rotating the angular, constant angular velocity, uniform angular velocity. Now we need to calculate the magnetic field at a particular time. Okay, so at a particular time, the theta will be how much is, let us take it's a omega t. Omega t at a time t is given. So that's what is we are trying to convey. The point where we should calculate the induced EMF means at a particular time it is moving with a certain angular velocity. So at that position, what will be the induced EMF? So the flux of the magnetic field at this time is, right? What is the expression for induced EMF is the minus d pi by dt. So first of all, we should understand, we should know what is phi here, what is flux here. So for that is the formula. Phi is equal to n BA cos theta. Okay, where n is the number of loops, B is the magnetic field, A is the area of the loop, and cos theta means it is the making angle with this magnetic field, right? So that's what substitute the values here. N is given in the problem n terms. The problem itself is given n terms, and magnetic field B is given. Uniform magnetic field capital B is there, and A is what? Just A is we assumed because it's a square, so all sides are equal. Then the area of that square will be A square, small a square, and substitute all the values. Theta is what? Theta. At what angle? At what angle we are trying to calculate this flux is? We assumed that at any particular time, moving with the angular velocity omega, then that will become theta here, right? Right. So yeah, substitute all the values. That induced EMF formula is E is equal to minus d pi by what? Dt. So what is pi here? Here n b a square omega sine theta means it's what is it? D by dt. No, now derivation here. So now we are derivating this one, that cos becomes sine and cos becomes sine and omega t. In that again derivation of omega t is omega. Yeah. So n b a square omega sine omega t. Now it is in which form? Sinusoidal form or alternating. Now there's an alternating EMF is induced in the coil, because within one complete rotation, how it looks like one where at one position it will be 0, at another position it will be maximum. So it's actually the sinusoidal change. So our alternating EMF is induced in the coil. Understood? So just it's a basic question, but more than this, toughest problems are also there, but only when we'll be very strong when if you are conceptually very strong. Okay. Right, now I'll proceed for one more problem. Right, here the figure shows the horizontal magnetic field, the similar kind of problem. The horizontal magnetic field, which is uniform above the dotted line. Observe this. A dotted line is here, and a long rectangular conducting loop of width L, width is given L, of mass M and resistance R, right? Conducting loop means definitely it's a metal, is placed partially above the partly below the dotted line with the lower edge parallel to it. So magnet lower edge is parallel to the line, okay, and whose dimensions are given. A, right? L is given, R is given, right? Whose mass is given. So whole information is given, but the thing is, the upper part of this loop just is immersed, just cross that dotted line. Now, with what velocity should it be pushed downwards? Yes. Now see, is actually it is in a magnetic field, right? This frame or a loop is the metallic one, so it produces its current, because while it is going means crosses this dotted line, what happens? The field is changing. Observe this. Field is changing. So while field is changing, what happens? The current will be generated in the loop. Then whenever the current is generated, then the particles experiences force, where the particles will be on this metal frame only, no. So there the force will be starts acting on it. Now, due to that force, either oppose or attraction takes place. Exactly, see, actually it will be opposes, because we studied Lenz's law and all, no, right? Faraday's laws we studied. So there what we studied, then always it is a opposite to the action, opposite to the reason, opposite to the formation. So here, while the frame is entering into the field, due to the induced EMF, the force acts on that, then force will be which direction? That's what here is the point. Now, what is asking? What velocity should be pushed downwards so that it may continue to fall without any acceleration? Actually, if there is no external force is there on the frame, the moment if you leave that, then easily fall down with the acceleration due to gravity. Understood? But what is asking? What velocity it should be pushed downwards so that it may continue to fall without any acceleration? Means without, means not much easily. Understood? Without any acceleration. Without any acceleration. Means just like that, if you push, just like that, it won't fall. Right? So, but at what velocity we need to apply so that both will be balanced, upward force and downward force will be balanced. So then what happens then if both the forces are balanced? Then what happens? External acceleration means acceleration won't come into the picture. So that's what he's asking. So now here is the solution. Let the uniform velocity of the fall be v. Initially, listen, initially it is frame is moving with the normal velocity v. Now the EMF is induced across the upper wire. Yes or no? So the moment it is entered into the field, then what happens? The induced EMF will be generated. Remember, before entering into the field, the velocity was v. Now the EMF is induced across the upper wire. Then its magnitude of induced EMF will be like this. What's the VBL or VBL? Now the current induced in the frame will be how much? Current is equal to, I told you it is V by R. So I is equal to V is nothing but potential, that is here. E is the EMF. Nothing but in the other language it is the EMF, potential only. Right? So here I is equal to VBL. Here V is the velocity, don't confuse. Okay, V is the magnetic field and L is the length of that or width of that loop. And R is the resistance of that metallic field. Now, so that, see, this is the current which is generated in the loop while it is entering into the magnetic field. Now, so that the magnetic force on the upper arm is, okay, so when it's entering into the field, then upper arm, see, opposing force will act on that frame. So how much it is? Bill is there, BIL. Okay, F is equal to BIL in the magnetic field. So I we have VBL by R. Okay, then in the formula itself, L is there, B is there. So it will be L square B square V by capital R. So this is the force in the upward direction. Because the object is moving downward, then upward force acts on it. Opposes, I told you, the opposes as per the Faraday's laws. And this force in the upward direction and yet the frame falls uniformly. And this force should balance the weight. Originally, it started moving with what velocity? V. The moment it is entering into the field, the external forces, a field is opposing the frame with a force is given here. V is equal, F is equal to V square L square by R. Then what is happening? This force is opposing the frame to move with the initial velocity. The initial is moving with the V, but it is not moving. Now it is not moving with the V, because the external force is acting. Now what is that for? What is that velocity? Now see. As the frame falls uniformly, this force should balance its weight. I told you, both the weight is what? Mg. Mg is always downward, but upward force is what? V square L square by R is acting. So both will balance. Then the force means the frame is not falling with the acceleration due to gravity. Why? Because upward force is acting on it. So both means the system is in equilibrium or it's not moving with the same acceleration due to gravity. Then upward force is equal to downward force. So here we have done that is mg is equal to v square L square by R. Then from that take out v. Then mgr by b square L square. Remember, all these are formula based concepts. Very, very, very important. Right. So this is about what? How to calculate the velocity. Now we'll move to the another problem. Angle AOB made of conducting wire okay, conducting a wire along a bisector through a magnetic field B as suggested by the figure. Find the EMF. So here is the figure, right? Find the EMF induced between the two free ends of the magnetic field is perpendicular to the plane at an angle. Observe this. Angle AOB is there, made of a conducting wire. Okay, AOB is a wire. Moves along, it's a bisector. Bisector means what? Perpendicular. Bisector means along the middle, exactly from the center. Through a magnetic field B as suggested by the figure, like this. So as shown in the figure, AOB, okay, from exactly at the center, they started moving with the velocity B. Observe the diagram. And both the arms are there. AO is one arm and OB is the arm. The angle between them is theta. So means making some angle. Now the whole system is moving in along the horizontal, okay, as shown in the figure with the velocity B. Now find the EMF induced between the two free ends if the magnetic field is perpendicular to the plane at the angle. Observe this, what the angle is making with the means the field is making with the plane, right? So find the EMF induced between the two free ends, right? What is the induced EMF at the two arms of this field they're asking? Okay, now we'll go for solution here. So yes, the rod OA, observe, is equivalent to the battery here because potential difference we are making here, right? Of EMF VBL, okay, right? VBL sine theta by 2. Observe the whole length is actually is given AOB and exactly at the center, that is called bisector. So the angle we're making half because it's a bisector. It's moving along with the V along the horizontal, right? We have seen the previous diagram, right? So now it will be what components like not components, sorry. So epsilon, that is EMF is equal to VBL sine theta by 2 is one arm and VBL sine theta by 2 for the another arm. Okay, so right, the positive charges of OA, shift towards A due to the force. Observe the force direction, and the positive terminal of the battery appears towards A. Positive terminal of the battery is towards the A, and similarly for the rod OB. Okay, and equivalent battery EMF is VBL sine theta by 2 went with the positive terminal towards O. So here, then only it is possible to make this bisector here. Right, the equivalent circuit is shown in the figure. Now here the EMF between points A and B is right, between A and B is asking. Between A and B. So it will be what, a 2B LV sine theta by 2. Clear? So this is what is the actually what is asking, find the induced EMF between the two free ends, that is A and B. Understood? And A is positively charged and B is negatively charged. So that's what is the total added, this one. So 2B LV sine theta. Clear? And now we'll move to the next problem. Yeah, here is the related to the solenoid. So the variation of induced EMF, E with the time t in a coil if a short bar magnet is moved along its axis with a constant velocity is best represented as yes, the variation, how we can represent, they're asking the variation. So variation of induced EMF with the time. See, it's very important because the induced EMF is varying with the time when the bar magnet is moved either towards or away. But here is given, see, look at this bar magnet is there, N is towards the coil or solenoid. Then what is asking, the bar magnet is moved along its axis with a constant velocity. How it can be represented? Okay, while the bar magnet is passing through the solenoid along its axis, then following or the representations, then how the variation that you can represent, variation of EMF of this, due to this solenoid, how you can represent while it is moving from one edge of the solenoid to the other, the magnet is moving through the solenoid. This is a problem. I hope you understood, right? While the magnet is going through the axis of the solenoid, then how the induced EMF changes. Here, right? Observe the diagram, observe the options, right? Now I will proceed for the solution. So, as the magnet moves, look at this, towards the magnet moves towards the coil. Observe, this is already see, it's almost what it's a theoretical based, right? There is no formula and all, theoretical based. So as the magnet moves towards the coil, the magnetic flux increases. Magnetic flux increases. Yes or no? Magnetic flux increases because we know the solenoid behaves as a normal magnet, and near the poles more flux will be there, and away from the poles less number of lines of force will be there. Now the magnet is moving towards the solenoid. The moment it is reaching the one edge of that, there more flux will be there. Okay, so the magnetic flux increases. And also there is a change in polarity of induced EMF. This is very, very, very important. While N is coming forward, coming towards the this one solenoid, then in what direction the current will be induced? There is a change in polarity of induced EMF. That's what is giving here information. There is a change in polarity of induced EMF when magnet passes. When magnet passes towards the solenoid, there is a change in what's the induced EMF will be changes in the solenoid. So that's what is asking. That's what is explaining here. There is a change in polarity of induced EMF when the magnet passes on it to the other side of the coil. So while it is traveling through and moving to the reaching the other side of the solenoid, so definitely there is a change. How the change will be? See, this solenoid while coming closer, it will repel. Remember, we studied the Faraday's laws. So, but forcibly we are sending it. Repel means what? The magnetic field decreases in the. It's like what's a diamagnet? Means repels means opposing. Force will be there definitely, but it will, which direction? Which way it is? Negative. And coming to other side of this one, what happens? Again, what happens? If of course it's the maximum, but is it's a moving away. Moving away means attractive power will be there. Attraction. Here it is coming closer. So while it is moving, means distance is decreasing and the magnetic field flux is increasing. Then what happens? The direction of polarity of this current will be increases, means changes, and reaches at a particular point. There it will be constant. That is zero will be there. Okay, because inside they already we studied in the other class that inside the solenoid the magnetic field is constant. Right, so then it is moving through. Then while it is coming out of that, then again actually the magnetic field is moving outward. Then what happens? The flux will be decreasing, but here the polarity of the other side of the solenoid will be changes. Then it will start attracting. Okay, so that's what is so only the possibility is B is there, because first is decreasing, means in the other way, means rejecting, that is repulsive, and the next one after reaching this side it will be attractive. Okay, so option B is your answer. Okay, how the electric field is changing with respect to time. Right, now we'll proceed for the next problem. Yes, just now we discussed the same concept. Just it's a problem is given on the same discussion. A current carrying solenoid. is approaching a conducting loop as shown in the figure. Now the direction of induced current as observed by an observer on the other side of the loop will be. This is very conceptual based, because the Faraday's laws, once you understood very strong, then you can solve such problems very easily. So that's why my request is be strong on the concepts, right? So here, the current carrying solenoid, okay, solenoid, observe this diagram, solenoid, approaching a conducting loop, right, conducting loop, right? Now the direction of induced current as observed by an observer on the other side of the loop will be, okay, understood? This is current carrying conductor or any conductor, while this magnetic field is approaching. Magnetic field is approaching, then what happens? There will be a change in magnetic field. Flux changes, no. So through the ring, the number of lines of force changes, and while it is coming closer, what happens? It will be increases. Okay, the number of lines of force will be increases. Then how it looks for the direction? Okay, the direction of the induced current observed by the observer in the other side of the ring or loop. Okay, so here is the solution. What's the answer actually is the clockwise direction. The clockwise direction. So clockwise direction is what south. Okay, appears as in south. Clear? Right. So here is an example. Here is an example. So yeah, we'll continue the same the problem with in the next class. Okay, as time's up, right? We'll stop here and we'll continue the same problem in the next class. Okay, so keep practicing. Thank you.